Hi everyone, I'm Brian Oberting from Argonne National Lab. Talk to you about the work to enable Raja, which is a portability layer that sits on top of other programming models for SYCL, basically to run on Intel GPUs. This is work from myself and also a lot of the Raja team from Lawrence Livermore. So as I think everybody knows it at this point in the workshop, basically the upcoming exascale systems are supporting heterogeneous hardware from a couple of different companies. So looking for Intel, AMD, NVIDIA. We need to have our scientific applications working across these. We have scientific applications already written in Raja. We need to be able to support these. So this is part of the reason like SYCL's become more popular is there's a lot of interest in having a portable programming language. Raja is another approach. Just kind of sits up at a higher level of abstraction where we sit on top of other programming models. So Raja is a bit of an overloaded term. So there's the Raja Portability Suite, which is a couple of different projects. And then there's Raja, which is like the execution layer. I'm going to focus on that. But first, I'll just introduce the overall portability suite to give everybody some context. So there's Raja, that's your performance portability abstraction. This is what kind of goes over kernel execution. This is basically, the idea is to have a single kind of application source that you don't have to mess around with whenever you're porting, but to have control over tuning knobs. So even if you're like using SYCL, if you're wanting to move to a different backend, you might need to tune your work sizes, things like that. The idea is to kind of separate that from the application kernel so you don't have to go in and kind of live with these multiple source files. And of course, like all abstractions, the goal is to have low overhead or no overhead. This is pretty much all implemented as a header library through template metaprogramming. So the goal is, zero cost abstraction ideally. Some of the related projects are Umpire. This is a kind of abstraction over resource management. So it's over resources. This is kind of a way for abstracting over like, give me some shared memory, give me device memory, host pinned, these kind of different abstract spaces. So you can have a single use case. Chai, which is a C++ array abstraction, which kind of gives you software support for unified memory. And then Camp is kind of a low-level metaprogramming facilities, gives you like tuple and some baseline resources. This gets used by the other projects. It's kind of like a common core underneath. I will talk a little bit about Camp, but for the most part, I'm going to be focusing on Raja. I think it's kind of interesting to discuss how things went for implementing a SYCL backend for this, because it's a abstraction over kernel execution in an abstract way. So there's kind of some interesting challenges, also some changes that ended up in Raja, basically from the experience working with SYCL that ended up helping kind of the other backend's performance. So it's an execution layer for simple or complex loops. So I'm going to show you an example with simple loop, which might not seem that powerful, but you can do complex loop nest, kind of a whole tree of loops with kind of arbitrary code in between, as many lambdas as you want to capture. And then you have control over how you're going to map all those out. As I said before, you want to decouple those loop bodies from the execution. So, you're writing your kernel code, your scientific code, but then the kind of control over how that executes gets put to another location. So this will be in a header file specified through the execution policy. So this allows you to kind of go in and tune for specific targets. So you can make pretty like substantial changes, go from like running a tiled OpenMP CPU execution to targeting the CUDA or SYCL backends without having to modify that kind of kernel launch, but just going in and including kind of a different execution policy header file. So just to fill everybody in case you've never seen one, so a lot of this is going to kind of familiar. So this is a basic Raja for all loop. So not doing anything too powerful here. The mapping, you can kind of see how this might work, but there's a few different pieces to it. First, the execution template for all, the common example, but not the most powerful. You also have like kernel that takes some parameters if you want to set up like shared local memory, things like that. Otherwise, kernel, you can take in like several different lambdas, include variables in between them. You can map from work groups to items. You can do tiling, you can do loop interchange, all these kind of things, and that would all just get specified in this execution policy. So here the one is pretty simple. This is saying run this as an OpenMP parallel 4, but these can get pretty complicated. I didn't want to put one up there just because seeing a bunch of lines of templating can be kind of confusing, but you can really do very powerful things with it. Then we capture our iteration space. This is pretty common. I guess the only thing here is that Raja does have support for kind of arbitrary indexes. You can just put together a set of random numbers that you want to visit, and it'll be able to take that. Obviously, your performance isn't going to be as good. And then we're capturing the loop body as a lambda, as all the portability layers are doing. So just to reiterate, we want clean encapsulation of the kernel code, easy customization of the kernel execution without touching the kernel code. It's also designed to be incrementally and selective adoption. So this means you don't have to port your entire application to Raja. You can go kernel by kernel. You can interface, like you can run CUDA code or SYCL code. Like I can run SYCL malloc to manage my memory if I don't want to use umpire. I can write a SYCL kernel and then also have other kernels in Raja. This is because it's all done through the headers, so it's all just compiling down to your backend. Obviously, when you do that, you have to make sure that that's included for the proper backend, so you kind of lose a bit of portability there. And allows for systematic performance tuning. So that's kind of the main thing here, is to give an abstraction, expose the tuning knobs that are important for applications, because we believe that when you move to a new system, you're going to need a tune for it. And you want to be able to do that without having too much overhead and having to go in and modify all of your kind of specific places. So kind of high level, this will probably look similar because that's how a lot of things work. But essentially you have an execution policy. You're going to include a policies for like my CPU, OpenMP policies. These are going to just be, using name for a template type. These are going to get passed in. It's going to go through the kind of header file backend for OpenMP, and then it'll work with any existing OpenMP compiler. So that's one of the kind of nice designs we have, and the kind of more pragmatic approach is that we can target whatever compiler is working for the system. So instead of kind of relying on compiler support, if need be, we can use a different backend. But if you have your application already written, you want to port to a new one, new backend, you just need to write out basically a new CUDA policies, which will be like how to execute your kernels. You can keep, you can declare things that just execute this sequentially on the CPU. As long as you have a compiler that can handle it, you can mix OpenMP with, I know it works with SYCL, so you can kind of fire off a few threads of OpenMP and then inside those launch SYCL kernels. And this can all be kind of templated out where you only have to include your execution policies. So you're not touching that application code. So talk today is about adding the SYCL backend in Raja, mostly for Intel GPU support because there's existing backends to support the other GPUs. Of course, SYCL is also portable, and we do test on AMD and NVIDIA, and everything works for the SYCL backend for that. Also, we kind of had some decisions. So there's a few different programming models that are supported for Intel GPUs. We decided to go with SYCL just because it's kind of very explicit. And with Raja, we want to have those tuning parameters be exposed. So it's kind of a natural fit to go with SYCL because you're already kind of having to control everything anyways. So since we're wanting to expose that, we're going to be controlling it. Okay. So this is kind of conceptually how things are going to map. It's a bit how you would expect. So for SYCL, we're creating a SYCL exec. We give it a work group size, and then there's a asynchronous or not option here, and that's going to be our execution policy, which we're passing into our for all. So I just go in, I define my new execution policies, and all my kernels are going to already kind of map over. So this kind of gets lowered down to an ND range. We always lower down to an ND range. This is because basically we decided we want to be able to control these. So I know at least for stencil application that I work with, it's super important to be able to kind of fine tune those work group sizes. So this is kind of conceptually how it's lowering down. You can kind of understand this, but obviously when you actually go into writing this, it's a bit more complicated. So this is actually part of the code from the SYCL backend. So I don't expect you to really get through all this, but I do want to call out a few different places. So this is just for the for all, not even the kernel, which has handling, multiple loop nests and kind of arbitrary amount of loops. A few things that kind of came in. One is we need unnamed lambdas. It's kind of important for these portability layers because everything's kind of going to the same location to get launched out. Then the other thing here is that we're specializing on whether or not our kernel, our lambda is trivially copyable. This is basically because if it's not trivially copyable, SYCL can't handle it, though we take an extra step and basically try to copy it over. We basically assume that it's device copyable. That's because that is the current semantics in the other backends. So we wanted to support that also. So it's a little bit slower because we're, allocating some space on the device and copying things over. But we're able to do this because we're already kind of going through a lot of templating. There's a few different concepts here. So they're kind of grayed out, but basically we end up with like 4 or 5 of these specializations that kind of have slightly different functionality. Some that handle reductions that I'll talk about a little later. The next kind of issue we had hit early on is this resource. So see here, we're getting our queue out of this SYCL resource, which is like a Raja type. And submitting with that, we're returning an event for it. Okay, this might seem kind of what you'd expect, but when you go back to the example, we're not passing in any resource here. There's kind of nothing set up for that. So there was kind of the question of, okay, what context should I be using, especially with Raja, where it's designed to kind of separate the concerns of kernel execution and umpire handles memory allocation. But now we get to the point where we need to make sure we can all access the same memory. So there's kind of a couple of solutions that came in. So this was from early on. First off, Raja has introduced a new API that takes resources. So this is partly to help the support be a little cleaner on the SYCL side, also to better support CUDA streams. So this starts looking more like a SYCL kernel where we're passing in basically, what resource or queue do you want to use. Alternatively, I mentioned CAMP earlier, compiler agnostic metaprogramming facilities. There's different resources. So there's SYCL resources, and through this, we implemented a default context. This is similar to the extension that Intel offers. I guess our one thing, I'm not sure if I don't think it's like that for the default context there, but we do in order. This is because we want to match the semantics from the other backends, and we don't want any kind of surprises coming for the users. So essentially, you can either pass through a resource or you kind of rely on using the CAMP default one. There is also a kind of extra API to just kind of set which resource you want to be using to Raja directly. This would be more like a CUDA set device kind of thing, because there were some implications for the other backends where they were relying on the runtime to give them this information. So that's in case you want to kind of create your own queues in your application, but you still want them to be able to play nice with your Raja kernels or even umpire. Okay. The next kind of challenging bit that ended up with some changes going into Raja, but also we leveraged some extensions for kind of one of our other ones is the reduction. Originally, Raja reductions were kind of designed, they really like to separate the concerns. So you basically created a reduction object that just got used inside your kernel, but there was nothing telling your kernel that it's doing a reduction. So this kind of creates some implementation challenges. So I know I created a reduction object. I can set something, say, hey, set up some shared memory maybe, but we don't really know because nothing's getting passed in there. It's just an overloaded plus equal operator, and then there's kind of functionality on the outside to pull out the correct value at the end. So I implemented support for this. It's very slow because we made the decision early on that we wanted to have a new API to kind of better support SYCL. Also, it would allow us to do basically improve performance for like OpenMP. We're able to leverage all the built-in reduction support. Additionally, it improve the other backends because they could make smarter decisions about the shared memory and, do more of a proper reduction. But this is supported as it is. But there's the new reduction interface, which looks more in line with what you see in SYCL or what you might see in the next talk. But here now the reduction is actually getting passed into the kernel launch. So we know that we're doing a reduction. This is one of the things that we're kind of specializing on for our templates, whether or not we have one of these objects in here, at which point we're just allocating a reduction object and then copying out the final result from that to this. So this basically allows us to leverage all the built-in support. Additionally, we could write a much better reduction just using shared memory if we wanted to write it manually. Yeah, just to play in on this one. This gets supported in the back end essentially just through doing atomic updates. Like I said, it's very slow. We improve it a little bit by using extension for kind of finding out where you are in the iteration space without having access to your index because it's just an overloaded operator. So that you can kind of split up the contention a little bit, but it was never kind of meant to be the performance one. So this is kind of the full list of things that are supported and also the policies that you can use to map things down. So I walked through for all, but kernel and launch are really where you get more powerful. These are where you can take multiple lambdas in, you have multiple loops. You can kind of map essentially these policies on the right are saying, how do you want to map your loops and your indexes? And you can kind of break things down, just groups, local. You can do the global where you get access directly with block sizes. And you can kind of interchange this. So like I said, you can do tiling where you can like map your groups to your tiles and things like that. You can really do some very nice complicated things. You can also, I know at least with the one API compilers we worked with, we're able to kind of do outer loop with OpenMP, launching SYCL kernels on the inside. We have asynchronous SYCL kernels and there's also the launch, which is very powerful, very complicated. I didn't want to get into it for the talk, but you can, this is using the hierarchical parallelism approach in SYCL. So we can kind of get some access to shared memory and work group barriers, things like that. You can write your kernel using. Okay, just want to quickly go through my evaluation. So my evaluation is I'm an abstraction layer over SYCL. I want to make sure I'm not introducing too much overhead. So there's a Raja performance suite. This is primarily developed by Rich Hornung. It's very good for compiler testing. Essentially, there's like built-in timers, correctness checking, but there's a lot of different variants. So basically, it's designed to write these kernels. So there's a lot of standard benchmarks. So you have polybench, alcal, stream. There's a bunch of application kernels in there. And just some like algorithms, basic algorithms kind of support. They're all kind of set up to essentially have a underlying programming model approach where you write what you would write directly in the programming model, and then the Raja version, which is designed to match that. Currently, we're working on getting things kind of lined up across programming models. This is because, so you can kind of set up to run, like I could compare the SYCL backend for just the base SYCL, which is like regular SYCL with regular CUDA or the Raja CUDA or the Raja SYCL all on AMD or NVIDIA. But right now, some of the kernels don't kind of execute the same way. They use like different work group sizes and things like that. So it's not a fair comparison. So when you do that, you have to go in and make sure that they're matching, which they kind of fell out of sync because the other backends kept developing while the SYCL one was not. So basically how this runs, it does run some warm-up kernels. As you're going to see when I get to the graph, there's a little bit of overhead. So you can specify what warm-up kernels to run because for us, we were loading from a cache. So we were taking a hit on the first version of the kernel that we ran, even though we ran some warm-up kernels because it wasn't touching everything. We're deciding right now whether I would just want to say with SYCL, everything is a warm-up kernel, run it all once just to make sure that we're not hitting any jitting or overhead. And then there's some recent introduction where it's templated, so you can kind of specify a range of work group sizes that you want to explore. So that's what I'm going to be presenting here. Essentially, there's a outer repetition loop with an inner submission loop. So you're going to get a lot of executions and checking for correctness. So this is kind of the default problem configuration of the box. So you see here the work group size 64. So just to explain the graph, this is the Raja performance relative to SYCL. So when the bar is lower, SYCL is faster. When it's higher, Raja is faster. Here, the orange bars are just from loading out of the cache because it's the first kernel that we're touching, and that's getting included in that outside timer. I will show kernel level performance through profiling a little bit later, and we see that's what it is. The main thing I want to focus here are on these ones where we are taking a significant performance hit using Raja. So three of these, the reducint, trapint, and dot, these are doing reductions. In Raja perf, currently it's using the old style reduction, so we're kind of expecting this because we're going in, we're doing atomic updates. We know it wasn't going to be performant, we weren't trying to be. They're currently being reworked to use the new reduction interface because as we saw performance improvements across pretty much all the backends, they decided to really start pushing the users to start using that interface. The other two here are Hydro 2D and Nested Init. And these are multi-dimensional or multi-level loop nests getting mapped to a kernel. And our performance is low here because we are making things fit properly in our ND ranges that we're setting up. So we're essentially doing some extra calculations. And with these, we're in a outer loop running repetitions. So we end up kind of paying that price over and over. So we're deciding whether we want to remove it right now. So theoretically, we want you to tune your kernel and tune it correctly so we can just kind of not handle this and let the runtime just say this is invalid work group sizes. So that's something we're kind of exploring. Then I just scaled up the problem size. So this is kind of showing, yeah, the overhead from that first touch kind of starts to go down, but otherwise performance kind of stays on par with what we were seeing before. Then I did some kernel level profiling. So this is the timing for the actual kernel, not including any of the launch overhead and the setup, especially that kind of extra overhead. So if you see in like Nested Init, Hydro 2D, now they're more on par. Turned out Hydro 2D was actually, through that calculation, picking some better work group sizes than the base one was doing, which ended up giving a little bit better performance. This was from iProf, which I'll plug real quick. It's from some of the developers who are here. This is part of THAPI. It's basically a simple way to get your kernel profiling results. So overall, we're mostly happy. We're deciding whether to drop out the kind of work group size fitting because the overhead shows pretty bad here, though it's kind of because it's set up for a benchmark suite. And then the reductions, we have tested them and they are much closer to basically if you do the SYCL reduction directly. The other thing that we explored with SYCL, which we were considering moving into the other backends, was whether or not we want to use just a range kernel ever. So rely on the compiler to make the decision. So we did implement with range for a lot of the SYCL kernels just to kind of explore it. Turned out it wasn't often doing anything too fancy or too nice, so we didn't think it was needed to expose it. So mostly because even though in SYCL it's kind of a nice easy mapping, if we expose like a auto kind of you decide for me what my work group size should be, it'd be nice to map down to SYCL, but then we want to support it for the other backends, at which point we need to implement some decision logic there. So ended up not including it. So in conclusion, essentially we got the Raja SYCL backend enabled. So we're running Raja applications. This is also working on AMD. We run some of the CI running on AMD. I've also tested on the Polaris system for NVIDIA. And then obviously for Intel, we're checking on Sunspot and Aurora. There's continued development happening right now. There's some missing features such as scans, kind of straightforward things that were not used by the applications we were looking at the time, but they're being filled in. We're also looking at potentially adding more tuning knobs. So one of the things we've kind of gone back and forth on is whether to expose a way to control your subgroup size, because that is something that I think we've seen from a few applications can be important for your performance. So we are considering whether to expose that as an execution policy that you can pass in through your template parameter to control. And then also the Raja Performance Suite. So the SYCL variants are being merged in and everything's being cleaned up. There's more kernels that are being implemented, some that need to be updated. So it's all going in right now. If you go to Raja Perf, download it, you'll get the ones that I listed here along with a few of the additional ones that have been updated recently. And that's all I wanted to talk about. And then my acknowledgements for DOE.
Hi, Brian. Thanks for the talk. How many applications are using Raja today?
So I don't know a number, but it's mostly applications at Lawrence Livermore use Raja. Externally, I know a couple that use Raja from Lawrence Berkeley. So the impression I have is, at least double-digit scientific applications, but Livermore's not as.
Thank you.
Science. So, how to phrase this? What are the areas in which you think Raja does things a little bit better than other portability layers that may exist?
So I really think it's the tuning options. So like being able to control basically the tuning, like not expecting the compiler. I mean, it'd be great if they can, but basically accepting that we're always going to need to be able to tune it for the new target. So how do we expose that while minimizing all the extra work that goes into, retargeting? And I think that's kind of the really nice design. Also, there's a lot of powerful things that they're doing with the templating, such as, you can do loop interchange, like just changing a couple of characters and, being able to do tiling and things like that, but without having to rewrite everything is very nice. But yeah, that's in my mind, the thing I'm most excited about with Raja is just having control over that without having to go in and really mess with the application kernel code.